In this lecture, I'm going to discuss another function called the error function. So the error function is related to a well-known function called the Gaussian function. So a Gaussian well, it's a distribution has the functional form of so it's 1 over this quantity sigma times the square root of 2 pi to the exponential minus x minus mu quantity squared divided by 2 sigma squared. So it looks kind of complicated, but if you plot it out versus x, what you get is the well-known bell-shaped curve. Now these parameters of mu is called the mean, and sigma is called the width. So mu is the mean, or basically where the maximum value is in the distribution, and sigma is the width. So if there is a very small sigma, then you would get a very sharp bell-shaped curve. Or if it's a very wide sigma, like this, you would get a much fatter bell-shaped curve. Okay. So Gaussian distribution is also sometimes called the normal distribution, and it is a distribution you get when you discuss random errors. So in the end, it's a very well-used probability distribution where you could integrate under the bell-shaped curve, and then it would tell you basically the amount of probability from one point to the next. So if I draw out my standard bell-shaped curve like this, there's a mean, but I could ask what's the probability of finding a value between x1 and x2, and so if I was to integrate under this curve, then that's going to give me the probability of some event occurring between x1 and x2. Now the nice thing about the Gaussian is that if you integrate the Gaussian from a range of minus infinity to infinity, it's a very easy integral to do. Now, integrating over the finite range is a little bit trickier, and so that's where it leads to this thing called the error function. So the error function, often written as ERF, is 2 over the square root of pi, the integral from 0 to x, e to the minus t squared dt. So x, the value that you're actually evaluating the error function, is one of the limits in the in this integral. So the interesting thing is that if we were to take a Gaussian function, which I'm going to label as capital Phi, and basically I would have square root of 2 pi right here, and let's say I want to integrate from minus infinity to x over the Gaussian function minus x minus mu quantity squared over 2 sigma squared, not t, I'm sorry, not x, but t. So that would be integrating over a Gaussian from minus infinity to x, and where now I'm using the dummy variable t. And so in the end, what does that mean? Well, what it means is that if I have a Gaussian like this with a mean of mu and a sigma as the width, and this is t, and so if I integrate from minus infinity up to a value of x, then what I'm asking is basically what's the probability underneath the distribution from everything from minus infinity all the way to some value x. So the interesting thing is that if I was to set mu equal to 0 and sigma equal to 1, then what I would get is 1 over the square root of 2 pi the integral of minus infinity to x e to the minus t squared over 2 dt, which looks a lot like the error function. And so this I could write down as the error function of, well, 1/2 plus 1/2 the error function of x over the square root of 2. And that's basically going to be equal to my Gaussian function for the one particular case of a mean of 0 and a sigma and a width of 1. So that means if I rearrange this and solve it now for the error function instead of the Gaussian, I would get 1/2 the error function, x over the square root of 2, is equal to the Gaussian minus 1/2. And so the error function is 2 times my Gaussian minus 1. Now there's another function related to it called the complementary error function. And that is defined, so it's usually labeled as ERFC as a function of x, is 2 over the square root of pi the integral of x to infinity of e to the minus t squared dt. What was I going to say? Oh yeah. So if I want to make this look like what we were talking about before, then the complementary error function of an argument of x over the square root of 2, I would get square root of 2 over pi, the integral x to infinity, e to the minus t squared over 2 dt. So the question is, why is this called the complementary error function? Well, if I was to take a regular error function and add it to the complementary error function, the value that I would get is, well, let's put this together. I would get 2 over the square root of pi, integral of 0 to x, e to the minus t squared dt, plus 2 over the square root of pi, the integral of x to infinity, e to the minus t squared dt. And so if I notice, I have basically the same integrand, and I still have the same factor of 2 over the square root of pi in front of both of them. So I would get 2 over the square root of pi, the integral 0 to infinity, e to the minus t squared dt, which so what I find is that this is a symmetric function, or it's an even function, and so I could take the 2, I would have 1 over the square root of pi, and take away the 2 and make that minus infinity to infinity, e to the minus t squared dt. And so what I'm doing is I'm integrating over the a Gaussian function in a range of minus infinity to infinity, where again the Gaussian function, where mu is equal to 0, sigma is equal to 1, but I'm integrating over this Gaussian function, and when I integrate over all space over my probability distribution, then the total probability is 1. And so what I find is that the error function plus the complementary error function, the sum of those two is equal to 1. And so that's why it's often called the complementary error function, because it complements the other side of the probability distribution. So the error function plus the complementary error function gives you the total space, and it gives you, in the end, a total probability of 1. Okay. So in that case, we can now start to look a little deeper at this connection of the error function and the Gaussian function. And so, okay, so what I have is I have an error function of x, and I basically rearrange the variables, so now I have 2 times the Gaussian distribution of x over the square root of 2 minus 1. If I was to say, look at the total range and say, what is the error function for an x is equal to infinity, then what I would get is 2 over the square root of pi, the integral 0 to infinity, e to the minus t squared dt, which in the end would give me 2 over the square root of pi times 1/2 times the gamma function of 1/2, which we looked at in earlier lectures, and the gamma function of 1/2 is the square root of pi. So in the end, what I get is the 2's canceling. The error function at infinity is the square root of pi divided by the square root of pi, or it's equal to 1. So basically, if I was to integrate the error function over the full space of 0 to infinity, the answer that I would get is 1.